Today, we are going to explore our Robotic Operating System version 2 or ROS2 development and specifically targeting on how to do uh, code analysis on top of this ROS2 development. We are not going to analyze the code of the ROS2 framework, but instead, we're going to analyze the code that you are writing on top of ROS2. I'm using an Ubuntu machine here, 22.04, but not included in today's demo was how I installed the ROS2 utility. I installed it in this location, and at the time of this recording, I'm using the humble release of ROS2. In order to bring in the ROS2 utilities into the active command line, you have to source this script here, setup.bash, after which the ROS2 utility will be made available in the terminal. The flow of ROS2 usually starts by creating an empty workspace, an ROS2 workspace, and inside the workspace, you create a package. And inside this package are the C++ code. A workspace can have many packages. I already have this example workspace with one package, and I'll just clone it from the GitHub repository. So this is the example workspace, which has one package, my CPP library. And the gist of this package is that it is a simple ATM example because our point here is to demonstrate how to do testing of this small code base. So let us start off by explaining how this code base is organized. So the car logic is defined by this interface. We have a savings account class containing a function to deposit, to withdraw, get name, get account number, and get balance. The implementation of this is here. Uh, so the implementation of get deposit would be here and so on. You can see here that if we withdraw and then if the balance is insufficient, we should get false and so on. The rest are just very straightforward. The library header.h and the myCpp library.cpp will be compiled into a static library. And the main execution of our app um, will be in this part here. It's rc main.cpp. So this is the main app instantiating the class with the initialization values and then calling one function and printing the result. The native or one of the frequently used unit testing tool for ROS2 development is Google Test. It is supported. I mean, it comes in naturally If we check the CMake of of the generated CMake of this package, we can see that this line here, find package amend CMake gtest, is operational in the ROS2 CMake script simply because ROS2 extended CMake to have Google Test support. Mm. You have to know that without such extension, you have to manually download the code of Google Test, manually compile it, and then manually link it into your executable in order to use Google Test. And because it's inherently supported in ROS2 CMake, the entire procedure just became a CMake script. But under the hood, the thing that I described, which is the compilation of Google Test and the linking, it is still happening, but we are not aware of it. So let's see the Google Test version of Google Test cases of this example project. The Google Test utility is a manual way of doing unit testing. So there's no way of automating it. So you have to manually craft the test cases. So the Google Test cases is this what we're looking here. So the the CMake of ROS2 package will build an instrumented Google Test executable, and when it is executed one by one, all of these cases here in the test block will be exercised for assertion, expecting that all of these will be true. If one of them will be false, then there will be a false assertion and a unit test failure. So this part here is manually uh, crafted. So you have to have knowledge of the class. You have first to know that the class exists. You have to know how to instantiate and pass parameters. Have to know invoking the function of the object, and understanding of what the return value is. Only then you can put an assertion. Like you can do this one should be true, this one should have the following value, and so on. So that is how Google Test uh, is done. For example, if we build this project here, you have to go back to the workspace root folder and then type Calcan build. If we check out the what's been in the build folder, we can see that this is now the class that we wrote, the C++ class in a static library. This is the main app, which is linking here, and this is the Google Test instrumented test cases, which is also linking from the library. If we run the Google Test, we can immediately see the all of the test cases have passed. You can see that everything is in green and okay. So Google Test is very simple to use. It can be complicated in some cases, but its initial entry is simple. Uh, for example, if one of the test case will fail, like say we deposit uh, 101 for some reason, and then we expect the balance to be 100, clearly failure in the test case. We do Culkin build and then run again the test case. and we can see that one of the test case has failed, and that is how Google test does it. It also return a status code of 1. Let's return back the let's correct back the code, and everything is successful now with a status code of 0 or success. So this is how Google Test does the unit testing. So it's important to take note that first, it is manually crafted. Second, Google Test that cannot do static analysis. Okay, and it keeps growing from here on, and manually adding more test cases. Now, let us try to check how Parasoft CC++ test unit testing and static analysis fits in the picture of ROS2 development. Uh, First and foremost, I have the Parasoft utility installed in my machine. Let me check the path. CPP test. So this is the IDE. You can also use Eclipse if the Parasoft is installed so plug in. That will also work. This is the native IDE of Parasoft. In addition to this, I also have the CPP test trace, which is just additional utility to generate the BDF. Now, all of these code base here that I just cloned does not have any Parasoft uh, configuration in it. It is purely ROS2 CMake uh, on code base. Because the Parasoft tooling natively understands CMake, we can one thing to analyze this through Parasoft tool is to go into the SRC folder and to go directly to the package. Okay, and then because CMake is an isolated build system, I can create a build folder here, go into the build, and then invoke the CMake. CMake there. The result of this is a generic makefile. And because the Parasoft tool has uh, very good integration with makefile. In fact, it is how the Parasoft tool generates BDF through a makefile. You can actually continue to generate a BDF from here by typing CPP test trace and CPP test trace output file. I will name this scan the PDF and then the make command. So this line here. There are other ways of integrating into CMake by modifying your existing CMake. And let me comment this first. What I mean is this one here I commented out is also another way of modifying your CMake in order to add Parasoft BDF generation. It's here, but you have to modify the CMake. The main CMake, you have to insert this include command and pointing it to where you installed your Parasoft tool and where to find the CMake extension integration file. Right now, I commented it out, but just a tip, if you go to CPP test where you install your Parasoft, Parasoft CPP samples, provided some project here wherein the use of CMake is demonstrated as well. Just if you want other references about it. I'll go back now to the ROS2. So I am currently commenting this out in this demo. I can't generate a PDF without it. So now let me go back to this command here and I will run this now. So we now have a PDF, and if we check the what source files were included in the PDF, we can see it has all the source files of interest. Uh, Coincidentally, it included the source files of Google Test, but we are not interested uh, of this, and we will delete this accordingly later on. Now that the PDF is generated, I will launch the IDE, um, CPP, uh, CPP test, and I will put it the workspace ROS2 in this path here, and check this, close this, and then create project, select C++ test, point it to the PDF that you just generated. Next, this one, scan PDF, open. If it says cannot automatically detect, just OK and then click again the auto detect and see it's now updated to GCC 11, which is the GCC version of my Ubuntu machine. Click finished. And from here on, we will be operating from the IDE. So like I said, we are not interested of the GCC code base because this is an artifact that was downloaded by CMake, the ROS2 CMake. So we are not interested of the GTest code base. I will delete this, delete there. And then let me see here. This one is also coming from the GTest. I recognize because I manually you are the manually created this. Okay, as you can see, it included the GTest header file, and these are the manually written GTest that we manually wrote. So we will delete this as well. So now what is left is the code of the package. We have the header and we have the implementation here, and we have the main executable that uses the library. Not cannot be done in Gtest or Google Test is the massive amount of static analysis that is available in the Parasoft toolset. It is massive. It is composed of, let me see, uh, here 4,562 because I'm using the older version. In the latest, I think it's around 5,008. Okay, so let us first do static analysis. It is something that Google Test cannot do. And let us click the parent node here, click And Parasoft does using static analysis. And despite there are only a handful of options here, you can create your own rules out from the 5,000 rule sets. So you can select a particular specific rule and create a new rule of your intention of your interest. In this demo, I'm just using the built-in rules called effective C++ and do static analysis. So it found three violations. If we click this and double click, because this report is interactive, so you double click and it will point you to the actual line. You can also right click and then view rule documentation, and it should open a browser to explain uh to give more I think I don't have a Chrome browser here, that's why it's not opening. You see. Yep. So it should open a documentation supposed to be. Yeah. Let's see. Or I did not set. Anyway, let's continue. Anyway, okay. So we have the static analysis and it's interactive. So we found three violations. We can't delete this and run again the code through another set of rules and it will find different violations. Let me try one more time. Let me try modern C++. 11 tasks reported. Interesting. So that's the power of static analysis in the Parasoft toolset. Let us go now to what Google Test previously was possible in Google Test by manually crafting the test cases. In the Parasoft way of unit test generation, uh, it will be auto-generated. So you would right-click here, Parasoft, test using uh, unit testing, generate unit test. So remember those macros in the test macro in Google Test, where you need to have to instantiate the class and call the member functions and then be aware of what the functions return should be and then put assertion. The PowerSoft can somehow automate 80% of this step. So let me show you generate unit test, and not only it can generate test case, it can generate this many versions the of the test case. Like in the withdraw function, it can generate 10 of them, and depending on the settings in the test configuration, you can generate more if the function signature can accommodate for several test cases. So double clicking this with row one, the PowerShell has automated the writing of these test cases. In the Google test, again, as I've mentioned, you have to be aware of how a class would be instantiated to call its member function and then reason about the return of this function and then make assertion. I mentioned that Parasoft only generated 80% of this because in the auto generation phase, such as this one, it does not contain an assertion. What is instead generated is a printf statement, a post condition. See? So Parasoft just printed what it sees, and then you have to be the one to decide if what is printed is correct and then manually convert this into an assertion. Let me show you how. So this is just the auto generation part. The next thing to do here is to execute the auto-generated test case, just like the Google Test Gmain instrumented executable. Um, Run unit test. And then because it will execute the test case, it will hit into the main app and the implementation of the library, it will hit into the lines there and show code coverage. As it stands now, if we go to the coverage tab, I think we hit 100% of the code base. Yeah, because it was a simple example. So we have 100% coverage. So the auto-generated test cases have covered everything in this particular situation here. And okay, the withdraw function, we have at this case where the balance is less than where the amount to be withdrawn is less than the balance, and we also have this case where there was insufficient balance and will return false. So the auto generation covered this scenario. So that's why we have green coverage there. Now, if we go here to the report here and let's go to the withdraw and show in task here. Let's see one of the post condition return false. Let me double click this and see this one. In line 1043, we are seeing here that we have an account object minimum of a float and then withdraw the amount, and then it says here it's returning false. Yeah, the minimum of a float is a negative number less than zero. If we go to the implementation of withdraw, obviously there was insufficient balance because it's less than the amount, which is zero when the object is initialized, and that is why we cannot withdraw. It's returning false. So if you think that this is an acceptable pass condition, you have to right click this here, and then from the pop-up menu, you have to select verify outcome. I will select verify outcome now. And notice carefully what happens to line 1043 above. as I select the verify outcome, and you can see here that line 1043 is now converted to an assert statement. This is now a test case. Prior to this, it was not a test case. So now that it is becoming a test case, any changes in this relationship or invariant will now flag test case error. So we can continue to do for the rest and one by one converting the post condition to become an assert condition. So if we go back to Google test here, so um, test here. So you have to manually write all of this in Google test. In Parasoft, everything is this is auto-generated with the minor change that you have to do the final assertion here by verifying the outcome, and you have to convert this into assert statement. Uh, Go back here. So you can see that in the auto generation, they're not assertion yet. They're post conditions, and you have to personally verify this on your own, and then convert them into a assert statement. This one, the name is zero. I mean empty string. The balance is zero. We draw a negative number. Return. Of course, the account name is empty. So on. So uh, the generated blocks of test here still intended to be modifiable by a developer, so you can continue to add more test conditions here, so that it just gives you a template, a skeleton, but still the intention is still to continue putting more logic inside. But like I said, with the basics of auto generation already covered 100%. So in a complicated code base, it may not do that. So that is why uh, these sections here still subject for manual uh, continuous changes and improvement. And so that covers the the method in which we can do unit testing and static code analysis of our ROS2 project in Parasoft tooling. The important thing to needs to happen is that we can generate a BDF file, and we can do that using the cpp trace and the make command, uh, the make file. Another way of doing that would be to use the this one, but this one is intrusive, as you will need to modify your make file. So the steps that I demo here is non-intrusive. Your make file will not be changed, but again, you have to to rely on the generated make file in the middle and build from there. That is all for this session, and